Hey everyone! Today we're going to build on the concepts that we've been talking about in the last few videos, and we're going to put together the whole Lagrangian of quantum chromodynamics. And after that, we'll also briefly explore some related topics like the strong CP problem, Gluon-Gluon Interactions, color confinement, and a comparison between the strong force and electromagnetism, which is also going to give us a good holistic understanding of gauge theories in general. Alright, well, let's pick up where we left off at the end of the last video, when we were talking about the field strength tensor for quantum chromodynamics. Now, the field strength tensor for the strong force, as we derived in the last video, is a rank 2 tensor in spacetime which encodes how the gauge field contains energy of its own. So we can write F mu nu equals partial mu g nu minus partial nu g mu plus Ig times the commutator of g mu and g nu. And as we demonstrated, because the spacetime components of the gauge field g mu live in SU3, the Lie algebra of SU3, it follows that the components of our field strength tensor, F mu nu, are also going to live in SU3. And as we mentioned in the last video, it's very interesting that the field strength tensor of electromagnetism has exactly the same form as the field strength tensor for the strong force, because we can write F mu nu equals partial mu a nu minus partial mu a mu plus I times Q times the commutator of a mu and a nu. And because the four spacetime components of the electromagnetic gauge field, a mu, live in the Lie algebra of U1, that is the real numbers, then it follows that the components of the electromagnetic field strength tensor also live in the Lie algebra of U1, that is, they're also real valued. Now, of course, in electromagnetism, because the components of the photon field are real valued, the commutator of a mu and a nu, which remember is just a mu times a nu minus a nu times a mu, is always going to be 0 because real numbers commute. And so that commutator term, you can imagine it being there, but it can never be anything because the components of the photon field commute. And so just as a square is a rectangle with no extension, the field strength tensor of electromagnetism is of the same form as for the strong force, but the commutator simply goes away. And that's ultimately because U1 is an abelian group. And so in practice, when we write the field strength tensor for electromagnetism, we simply write F mu nu equals partial mu a nu minus partial nu a mu. But there's a problem. The field strength tensor is a rank 2 tensor in spacetime, right? Because it's mu nu, you can write it as a 4x4 array of numbers for each possibility of mu and nu. And moreover, the individual spacetime components of the field strength tensor are Lie algebra valued objects. For the electromagnetic field strength tensor, that just means they're real numbers, but for the field strength tensor of QCD, that means they're SU3 matrices. And the problem is that when we're writing a term in our Lagrangian, we need real scalars. Not these rank 2 tensors with the Lie algebra valued components. No, we need some real scalars. That's what you make a Lagrangian out of. And so the question becomes, how do we sum up the total contribution to the Lagrangian from the field strength tensor? In other words, we need to find an expression involving F mu nu, which has all the properties that we would expect in a term in our Lagrangian. For example, it has to be Lorentz invariant, meaning that all inertial observers in different reference frames can agree on the value of that number. It also has to be gauge invariant, which means that regardless of whatever SU3 transformation we apply, that is, regardless of our gauge conditions, we can't be able to change this part of the Lagrangian just by hopping into a new gauge. No, it has to stay constant across all gauges. It also has to be real valued, meaning a scalar, but not like a complex scalar. But no, it has to be a real number in order to be properly behaved for a Lagrangian. And then ideally, and this is not strictly a requirement of gauge symmetry, but ideally, it should also be kinetic, meaning that it's quadratic in our fields and derivatives. Now, strictly speaking, it is possible to imagine higher order terms that don't violate local SU3 symmetry. But typically, we don't go beyond the quadratic terms because they don't matter. And they're also super tricky to work with mathematically, so And we touched on this in the electromagnetism video when we asked how come you couldn't have like f mu nu squared or, to a higher power. And then ultimately the answer was, well, without those, you can derive Maxwell's equations and, that's what's observed, especially in the low energy limit, so that's all good. Okay, so now to answer this question of how can we go from the field strength tensor to the way in which it contributes to the Lagrangian, I want to just look at exactly what we did for electromagnetism and then simply copy and paste. So the philosophy there is that if we go way back to part 1, we talked about how the magic bean of U1 symmetry sprouts into electromagnetism, and we talked about how the magic bean of SU3 symmetry sprouts into the strong force. And so we should expect a deep structural similarity across both electromagnetism and the strong force, with the only difference being swapping out the U1 symmetry group for SU3. And also a difference in the strength of the coupling constant. That's also allowed. But other than that, electromagnetism and the strong force should be basically the same. And so this gives us a convenient shortcut for constructing QCD. We just copy and paste what we did for electromagnetism and then check our work. All right, so for electromagnetism, we found that the photon part of the Lagrangian is -1/4 f mu nu. Now that's in natural units. In Gaussian units, you have a -1/16 pi. And that's just a different normalization convention depending on the units that we're using. The main thing is that it's f mu nu. And the reason we came upon this expression out of all possible expressions that we can make out of f mu nu is that this is Lorentz invariant, because both mu and nu are properly contracted. So we have the downstairs mu nu and we have the upstairs mu nu. That is the Lorentz covariant field strength tensor, as well as the Lorentz contravariant field strength tensor. So as you hop from one inertial reference frame to another, the product of those things with the downstairs and the upstairs is going to be constant for all observers. So that's good, we're not in violation of special relativity, okay? Einstein is happy. And then, of course, you can also show that this expression is gauge invariant because it takes on the same value in all gauges. And when it comes to electromagnetism, that's actually kind of a trivial result because all the components of f mu nu remain the same in all gauges. Now, for QCD, it's a little more tricky because from one gauge to another, f mu nu undergoes an adjoint transformation. That is the UU dagger sandwich, where it reorients itself in color space. And so in a moment, we'll have to put in a little bit of work to prove that our Gluon-Lagrangian term is actually gauge invariant. Okay, and so the next good thing about the photon's contribution to the Lagrangian of electrodynamics is that it's real valued. The reason being, in electromagnetism, the components of the field strength tensor are all real numbers. And so each f mu nu is real, and so therefore, when you're summing over all these f mu nu, that's going to be a real number. And then the last nice thing about this is that the expression is kinetic, meaning that you end up with quadratic expressions. And so that's all good. Now, if you reflect on what we just looked at here, none of this is really about local U1 symmetry per se. Right? You think about QCD and you think about how it's a gauge theory, and so it demands much the same structure. So therefore, look, here's what we're going to do. We're simply going to say that the gluon part of our Lagrangian is going to be -1/4, and then it'll be an f mu nu, but on each expression we'll have the index a, which runs from 1 to 8 and corresponds to the generators of SU3. So in other words, all we're doing here is we're taking exactly the same expression for the photon's contribution to the Lagrangian in electrodynamics, and we're saying that is going to be precisely the gluon's contribution to the Lagrangian of chromodynamics. And the only difference is that we have 8 gluon fields instead of the 1 photon field of electromagnetism. See, because in this expression, we're summing over A. So we have 8 f mu nus all added up, one for each value of A. And now one question that comes up is, hey, are we sure that this is a legit move? Are we sure that we don't have to account for any kind of special differences regarding the non-abelian nature of SU3 relative to the abelian nature of U1? And the answer to that question is that actually, no, it's all good, because remember that baked into the definition of the field strength tensor for QCD and for any non-abelian gauge theory is that commutator term that already captures the interactions of the gauge field with itself. So the differences between an abelian gauge theory and a non-abelian gauge theory regarding the field strength tensor and the Lagrangian term, all the gauge field self-interactions are already baked into the definition of the field strength tensor. And remember, they have to be, because as we derived in the last video, you need the 6 more ways in combination with the 6 ways in order to end up with a field strength tensor which transforms correctly from one gauge to another. Okay, now it also has to be said that this expression shown here, which I do think is best thought of as simply a sum over all the f mu nus for each of the 8 gluon fields, can also be written as 1/2 the trace of f mu nu, where now the f mu nus and f mu nus are the SU3 matrix-valued fields. So if you want to, you can think about the Lagrangian term in terms of those matrix-valued field strength tensors. It's up to you. These things are mathematically equivalent. And you can prove that these things are equivalent because if you ask the question of what is the trace of f mu nu, well, if you take each of the matrices in that expression, write the Lorentz covariant field strength tensor as f mu nu A, and then write the Lorentz contravariant field strength tensor as fb mu nu, in other words, just simply write each of the SU3 matrix-valued objects as a linear combination of some scalar-valued field strength tensors times the generators of SU3, then you can go ahead and pull those scalars outside of the trace, and then you end up with an expression involving the real-valued field strength tensors times the trace of the generators of SU3. And then one of the properties of the generators of SU3, as we've defined them, being half of the Gell-Mann matrices, is that by definition, we have that the trace of the product of TA and TB is going to be equal to 1/2 if A equals B, or 0 if A does not equal B. Okay, so this is, in other words, 1/2 the Kronecker delta. And when you think that through, what that means is that all these terms are going to go away, except for the ones where A equals B, and so then that expression reduces to 1/2 f mu nu A, fa mu nu. And so when you see that the trace of the matrix-valued f mu nu is equal to 1/2 of the sum over the real-valued f mu nus, then you can see that the 2 versions of L-gluons that we've written here are actually exactly the same thing. Now, the reason I bring up this trace expression is that often it's easier to work with that form if you want to prove something or if you want to examine or generalize these ideas. It's very useful to know that trace expression. But in terms of visualizing it and thinking about it, I think the best way to imagine the gluon part of the Lagrangian is simply as a sum over the f mu nu for each of the 8 field strength tensors. All right. Well, I want to take a moment to show that the gluon part of the Lagrangian, that is -1/4 f mu nu A, fa mu nu, is indeed gauge invariant. And there's a way to show this algebraically using the trace and matrix-valued expression for L-gluons. But actually, I want to imagine it in terms of the form shown here with the sum over the 8 different field strength tensors, because I think this way of looking at it is more visual. So the thing to keep in mind is that we can imagine our SU3 matrix-valued field strength tensor, f mu nu, as the sum over 8 real scalar-valued field strength tensors, f mu nu A, each one multiplied by a SU3 generator, TA. Right? So f mu nu equals f mu nu A TA. And all we're saying there is that the space-time components of f mu nu live in SU3. And so therefore, when we hop into another gauge, the space-time components of f mu nu are going to rotate in SU3. They're going to undergo that adjoint transformation that properly reorients them in color space, as we proved in the last video. They're going to go into that UU dagger sandwich. Now this term f mu nu A, fa mu nu, think of that as a dot product in the 8-dimensional real space of SU3 coefficients. And so therefore, under a gauge transformation, as f mu nu rotates in SU3, the individual values of f mu nu A are going to change as f mu nu rotates in color space, but the dot product is going to remain invariant under that rotation in color space. And so therefore, the gluon part of the Lagrangian is going to be gauge invariant. As you hop from one gauge to another, f mu nu rotates in color space, but the magnitude of this term, the magnitude of this sum, this dot product, is going to remain the same, regardless of which gauge we are in. All right, well, now that we know how our field strength tensor contributes to the Lagrangian of quantum chromodynamics, let's take a minute to reflect on how far we've come and look at all the things that we've derived from local SU3 symmetry. So we started out with a quark field, psi, which we've thought of as a color triplet field. Now, even though the color triplet field is actually 3 Dirac bispinor fields, we've been thinking about it purely in terms of that color degree of freedom, and so effectively we're imagining a triplet of complex numbers. And then as a way of transforming that triplet field, we brought in the concept of an SU3 matrix field, where at each point in space and time, we're able to rotate our quark field in color space by arbitrary amounts. And then we saw how, oh no, that's going to create a whole mess and it's going to mess up our whole description of what's going on. And so then we thought about it for a while and we realized, okay, we got to bring in a gauge field to come in and clean up that mess. That gauge field is going to necessarily live in SU3, the Lie algebra of SU3. When we thought about SU3, we encountered our friendly octopus, and that taught us that we can always trade a SU3 matrix for 8 real numbers. And so therefore, if the space-time components of our gauge field live in SU3, we know that we can think about that in terms of 8 real-valued 4-vector gauge fields, the gluon fields. And then meditating on the color triplet field psi and the gauge field g mu, we realized, okay, cool, we can put together a Lagrangian which has local SU3 symmetry, because as we transform psi, the gauge field is going to transform itself in the appropriate way in order to clean up that mess. So that's all fine and good, but then we thought, hey, wait a minute, we need to give the gauge field a life of its own in order for this to be credible and to make good physical sense. And so in part 4, we derived the concept of the field strength tensor for the strong force, and we found that it's very similar to the 6 ways of electromagnetism that we know and love, but with a non-abelian upgrade that brings in the commutator of the gauge field. And then, having explored the definition of this field strength tensor, we realized, hey, wait a minute, because our gauge field lives in SU3, then when you look at how the field strength tensor is defined, necessarily the spacetime components of f mu nu also live in SU3. And what do we know about things that live in SU3? You can write them as 8 real numbers, thanks to the octopus. So then we have this notion of 8 real-valued field strength tensors for QCD. And these can be indexed with A running from 1 to 8. And you can think of the 8th real-valued field strength tensor as being basically the 6 ways of the 8th gluon field. But there's also going to be a term which brings in all the other gluon fields in proportion to the SU3 structure constants. And so you end up with this interaction term in the definition of the field strength tensor. And that causes a whole lot of problems in QCD. It makes the math really difficult to work with. But it is what it is, we can't choose how it is, that's just how it be. Okay, and so when you reflect on all of this and you look at the gauge transformation rules, we have the transformed color triplet field psi is just simply U times psi for our SU3 matrix U. The gauge field from one gauge to another goes into the UU dagger sandwich of the adjoint transformation, and that represents a kind of reorientation in color space which is appropriate given the SU3 transformation. And then in addition to the adjoint transformation, it also picks up this derivative term, I over g partial mu u, u dagger, and that's the thing that comes in and cleans up the mess, having to do with the local nature of our SU3 transformation, and all the gradients of a mess that we're able to make in space and time. The derivative term in the gauge transformation rule is going to come in and clean up that mess. And then as we saw, sort of by definition, the field strength tensor in the new gauge is simply going to undergo that adjoint transformation, so it's only going to go in the UU dagger sandwich and is otherwise completely unaffected. And as we saw in the last video, essentially what that means is that in every gauge, the field strength tensor preserves its identity. It's really the same thing in every gauge. And so that adjoint transformation is really just a correct reorientation in color space, because we're changing what we mean by color space when we apply the local SU3 transformation. Okay, and now finally, as we've seen just a few moments ago, we can account for the way in which the field strength tensor contributes to the Lagrangian in exactly the same way as we did for electromagnetism, the only difference being that now we have 8 real-valued field strength tensors, and so we're going to have 8 of that -1/4 f mu nu in our Lagrangian. And so finally, we've assembled the full QCD Lagrangian, which contains the Dirac-Lagrangian, which describes the kinetic and mass energy of the quark field, psi. We also then have the interaction term, which describes the interaction between our matter field and our gauge field. And then finally, we have this term which describes how the gluon fields themselves contain their own energy. Now, there is a little caveat that we'll get to in just a moment relating to the strong CP problem and the theta term in the Lagrangian. So we'll talk about that briefly in just a moment, but for now, the Lagrangian you see on your screen here, this is the famous Lagrangian of quantum chromodynamics. And really, the whole purpose of this video series is to show you why that equation is what it is, you know? We started off with the magic bean of local SU3 symmetry. I told you it was going to blossom into the strong force. And I hope that in this video series, I've laid out the argumentation of why that is actually the case, so that you can see, okay, yeah, the foundations of quantum chromodynamics can indeed be derived from local SU3 symmetry. So in a way, this is the end of our adventure, but in another way, it's also just the beginning. Right, because normally when you're doing physics, the Lagrangian is taken as kind of a starting point, you know, it's almost axiomatic. And so everything we've been talking about in this video series is kind of underneath the foundations that you normally take for granted. And so we're kind of far removed from practical applications, but I hope that philosophically you found this to be a helpful meditation. Okay, now there is a very difficult mystery that we're not going to address today, but that I do have to mention in passing, because I know if I leave this out of the video entirely, I'm going to get 1,000 comments like, hey, why didn't you bring this up? So I'm going to bring it up, but we're not going to get into it in depth, because going into it in depth would take like many, many hours. This topic would make for a great video. In fact, I'd like to do a video on this someday, but it really needs to be its own topic, because it's a huge, huge topic to do it right. Okay, so this is going to be like a super, super fast summary of a thing, all right? So we're not going to go into this in depth. The thing is this. In theory, we ought to be able to add the following expression to our Lagrangian. We'll call it L theta, where this equals theta over 2 times g over 4 pi squared times f mu nu a, f tilde a mu. Now all that stuff in front of the f mu nu, that's just a constant. Theta is a parameter that sets the strength of this term in the Lagrangian, and then g is our good old QCD coupling constant. So the only thing here that's new, that's kind of interesting, that we haven't talked about in this video, is this f tilde. So what is f tilde? Well, this is something known as the dual of the field strength tensor. And if you want to read more about that, you can check out Quigg 8.11.5. We're not going to go into depth on it today, but the main thing that I want to point out is that this expression, L theta, it's Lorentz invariant, it's gauge invariant, and it's real valued. So we have no good theoretical reason to exclude it from the QCD Lagrangian. So when we're constructing QCD from scratch and thinking purely in terms of local SU3 symmetry, and someone comes along and says, hey, you should add this term to your Lagrangian, we can't say, no, get that out of here, we don't want that. Because if you investigate it mathematically, which we won't do today, but if you did, you would show, yeah, okay, Lorentz invariant, gauge invariant, real valued. All right, that should be there in our Lagrangian. But it's deeply troubling, this term, because it violates parity and charge parity symmetry. The reason that is that an expression of this form is going to be proportional to the dot product between the color electric and color magnetic fields. So you add up over each A equals 1, ... 8. For each of those, the color electric and color magnetic field, dot product those together, add them all up, that's going to be proportional to this L theta term. But now if you think about electric fields and magnetic fields, the electric field is a vector, the magnetic field is a pseudovector. So under a parity transformation, your electric field is going to switch around. You know, it's going to pick up a minus sign, but the magnetic field, being a pseudovector, is not. And so therefore, the dot product of the electric field and magnetic field is collectively going to pick up a minus sign under a parity transformation, which is no good, because you don't want a number that becomes negative under a parity transformation. That's weird. That violates parity symmetry. And you might think that, okay, maybe to save the day, perhaps this doesn't violate charge parity symmetry. Like maybe if you do a parity transformation and also change what you mean by charge, change the sign of the definition of charge, maybe that would restore the symmetry. But it's like, no, actually it doesn't, Because if you think about the dot product of an electric and a magnetic field, switch what you mean by charge, your electric field is going to go the opposite way now, but so is your magnetic field. And so in this expression, you're going to get a minus times a minus, so it's a plus, so there's actually no change to this expression, whether or not you switch your definition of charge. And so this expression actually would violate charge parity symmetry, which is very weird. But on this basis, we can say that theoretically, if we're building a gauge theory based on local SU3 symmetry, then in principle, it is possible to have a term in our Lagrangian which violates charge parity symmetry. It's very strange. But now here's the mystery. Experimentally, quantum chromodynamics does seem to preserve charge parity symmetry, as far as anyone can tell. In other words, we know that the absolute value of theta has to be a super, super tiny number. But why is theta so small? What makes it vanish? What principle says, even though we should expect this expression to exist, for whatever reason, it's vanishingly small? Why? We don't know. And so this is known as the strong CP problem. So that's the deep mystery, is theoretically, the strong force should be able to violate charge parity symmetry. For whatever reason, in practice, it seems not to, and we really don't know why that is. Probably the most promising solution is the concept of axions, and that's a whole nother rabbit hole we can go into, but we're not going to go into that today. Anyway, I just wanted to bring up the mystery of the strong CP problem and this theta term in the Lagrangian. I know this was a super fast, very cursory view of it, and but anyway, like I said, to do justice to this topic would take many, many hours. So we won't be going any further on this topic today. All right, now let's look at how the gluon part of our Lagrangian implies Gluon-Gluon interactions. So to do this, all we have to do is write the gluon part of our Lagrangian in terms of the real-valued gluon fields G mu A, where mu is the spacetime index, and A is the index that corresponds to the generators of SU3. Well, as we saw earlier, we can write our scalar-valued field strength tensors in terms of the 6 ways of the gluon field minus G times the structure constants of SU3 times the product of the components of all the other gluon fields that correspond to the same spacetime indices mu and nu. And remember, that result arises inevitably from local SU3 symmetry. Remember how we derived the field strength tensor from the 6 ways and the 6 more ways, and we saw that's the only way it can be. Okay, so now all we have to do is use that expression for the scalar-valued field strength tensor to evaluate our gluon Lagrangian in terms of the real-valued gluon fields. Because then we can see exactly how energy is contained in each and all of the components of the real-valued gluon fields. And if that equation depends on the product of one gluon field component with another, then that's an interaction term, because that implies that there's energy associated with both of those components existing together. All right, so all we've done here is substituted F into the definition of L gluons, being mindful of the downstairs and the upstairs spacetime indices so that the whole thing contracts properly. Now, another thing we have to note here is that on the right side of the expression, notice that we have the indices A, D, and E on the SU3 structure constants, and the indices D and E on those gluon fields. The reason being that if you look in the definition of the real-valued field strength tensor, you find that for the 8th index, you end up with the 6 ways of the 8th gluon field, but then minus this combination of all the other gluon fields. And so when we multiply these terms together, it's okay that the A index is the same on the 6 ways part of the expression, but it's important to have those different indices on the part of the expression where we're summing over all of the other possible gluon fields, so that in both of these versions of the field strength tensor, we're doing a complete unrelated sum over all of the other possible gluon fields. See, because if we just used FABC for both sides, then there would be like this connection between those two sums that isn't warranted, okay? Each sum should be totally independent. All right, well then the next thing we have to do is simply to multiply everything out. So we have 3 things times 3 things, and we'll end up then with 9 things. which is what I've shown here. Now, this is quite messy, but you can see based on the color coding how everything comes together. And I've written it in kind of a simplified way. And although this looks extremely messy, bear in mind, this is just basic algebra. We're just multiplying things together. But now, check this out. If we color code it like so, we can see that these green terms have to do with the gluon's kinetic energy, because those are just derivatives of the gluon field. And in that expression, because the index A is repeated, you can read this green term as a sum over all of the different possibilities for A. So copy and paste that green expression 8 times for A being 1, 2, 3, ... up to 8, and that is how the gluon fields contribute kinetically to the Lagrangian. And by the way, that's basically just 8 copies of the way the photon field contributes kinetically to the Lagrangian of quantum electrodynamics. So when you think about the field strength tensor in QCD as being sort of like 8 copies of the electromagnetic field strength tensor, that's true insofar as the gluon Lagrangian is this green term. But in QCD, we also have these orange terms and these blue terms. Now, the orange ones are 3 gluon interactions, and you can see that because each of those expressions involves the product of 2 gluon fields along with the derivatives of a 3rd gluon field. And if you look at the blue term, you can see even more directly how that's a 4 gluon interaction, because you have the product of 4 different gluon fields. And so this is why, when you really get into QCD, and you start busting out the Feynman diagrams, you're going to encounter these 3 and 4 gluon vertices. But you're not going to find a 2 gluon vertex, or a 5 gluon vertex, or a 6 gluon vertex, but no, just 3 and 4. And the reason for that, if you're ever wondering why it is, you don't have to wonder anymore, because we've just shown where that comes from. It has to do with the way the gluon fields naturally contribute to the Lagrangian, which can ultimately all be traced back to the nature of local SU3 symmetry. Isn't that an amazing thing? I just think it's wonderful. Speaking of those Gluon-Gluon interactions, those are actually the cause of the mysterious phenomenon of color confinement. See, the way that it works is that the Gluon-Gluon interactions in the gluon part of the Lagrangian are going to make the gluon fields kind of sticky. And so the gluon fields are going to have a tendency to pull together into gluon flux tubes between the quarks. So when you have some quarks that are in a bound state, the gluons between them are going to tend to pull together into these gluon flux tubes. And those you can think of as like springs, where the more you try to stretch them out, the harder they pull back in. And that has the effect of confining the quarks into a color-neutral state. And you see how the quarks have no way to escape the situation. Try to pull them farther and farther out, and the gluon flux tubes are going to pull them harder and harder back in. And by the way, in these very high-intensity particle collider experiments, you can put so much energy into the situation that you end up stretching quarks so far out that the energies involved get so high that you can actually create a new quark-antiquark pair out of the vacuum. And so even if you did stretch the quarks far enough apart, at some point the situation is going to get so intense that you're just going to end up creating more quark-antiquark pairs, and you're going to end up with more bound states of quarks getting split off from each other. But each bound state is going to remain color neutral no matter what. And that's the principle of color confinement. That's why every bound state of quarks looks color neutral from a distance. And that's why quark color has no place in the world of conventional sanity. It's not an effect that's able to emerge up into macroscopic scales. No, quark color remains confined at the subatomic level. And by the way, it's worth pointing out that we don't see this effect for electromagnetism because the U1 symmetry group that electromagnetism is based on is an abelian group. And so the commutator of A mu and A nu is always 0. Therefore, in our field strength tensor F mu nu, even if you imagine that containing a commutator term, well, it's an abelian group, so the commutator is 0, and so therefore in the photon part of our Lagrangian, we're not going to have photon-photon interactions, and so that's why the photon field is not sticky in this kind of a way where it wants to form these flux tubes. But QCD is based on local SU3 symmetry, which is non-abelian, and so it does have a non-zero commutator term in the field strength tensor, and so we do have Gluon-Gluon interactions. And one of the interesting things about QCD is that technically there doesn't yet exist a rigorous proof starting with the Lagrangian of quantum chromodynamics, which proves that for sure color confinement is inevitable under all circumstances. However, lattice QCD computer simulations strongly suggest that this is the case. So before you go thinking, hey, that's an unsolved problem, I'd like to solve it, just realize that the reason it's unsolved is because the math is incredibly messy and difficult to work with. But between lattice QCD simulations and this story about sticky gluon fields, the apparently mysterious phenomenon of color confinement becomes a lot less mysterious. We can very confidently state that the origin of color confinement can be found in the non-abelian nature of SU3. If you want to read more about the confinement problem, I'd recommend the book An Introduction to the Confinement Problem by Jeff Greensight. This is a very advanced book, suited for grad students and professionals, but it's written very nicely. It's one of those things that's very fun to read. Jeff is a great author. One other thing I'll briefly touch on, even though in part 1 I told you we wouldn't touch on this, but we'll touch on it very briefly, is the running of the strong coupling constant. So the strength of the strong force is set by the strong coupling constant, which we can write as alpha S. And all alpha S is our coupling constant g squared divided by 4 pi h bar c. So in natural units, alpha S is just g squared over 4 pi. So it's basically just the coupling constant squared. And this parameter is actually not constant, but it depends on the energy scale of the interaction. So as you can see in this chart, if we plot the strong coupling constant alpha S on the y-axis, and we plot the energy scale Q on the x-axis, then you can see that at higher energies, we have a lower value of alpha S. Now, one of the numbers that's often quoted for alpha S is about 0.12, and that number you get at energy scales of about 100 GeVs, which is approximately the Z boson mass. So that's a very important energy scale in particle physics. But as you can see in the plot, at low energy, which corresponds to longer distances, alpha S is very high. And that pertains to color confinement, because if you think about stretching out a couple of quarks to long distance, the strong force really wants to pull those quarks back together. And then conversely, at high energies, corresponding to tiny distances, alpha S becomes very low. And that's the phenomenon known as asymptotic freedom. And the reason it's called asymptotic freedom is that in the limit of super high energies, right, in the asymptote as this chart goes out to the right all the way to infinity, you'll end up getting an alpha S which approaches 0, meaning that if you imagine two quarks that are smushed right up next to each other, super duper close, ultra high energies, then the strong force actually becomes weaker as they get closer together. So that's what people mean by asymptotic freedom. Now for reference, we can compare alpha S to the fine structure constant of electromagnetism. And in electromagnetism, the fine structure constant is defined in exactly the same way. We simply take our coupling constant squared divided by 4 pi h bar c. Oh, I should point out, this is a dimensionless number. And famously, in electromagnetism, the fine structure constant is approximately 1 over 137. No one knows why. This is a big mystery, what's the deal with 137? No one knows. And for what it's worth, the fine structure constant also runs with the energy scale of the experiment to some extent. But 1 over 137 is in the low energy limit. Now one thing you'll notice is that 1 over 137 is a very small number. And because it's so much less than 1, if you imagine alpha squared, or alpha to some higher power, very quickly it becomes a very, very low number as you increase the power of alpha. And so when you're doing calculations involving Feynman diagrams, the smallness of alpha is going to suppress your high-order, highly contrived Feynman diagrams, and so those become irrelevant compared to the simpler Feynman diagrams which dominate the interaction. And that makes quantum electrodynamics a perturbative theory in the sense that all you need to do is calculate some lower order Feynman diagrams, and you can neglect the higher order ones because their relevance is going to be suppressed very quickly by the smallness of the fine structure constant. However, if you look at the strong coupling constant, with its value of, say, 0.12 at 100 GeVs, well, that's like an order of magnitude bigger than the fine structure constant. And if you go to a lower energy scale, you get even higher values of alpha S. So that becomes a problem, because in QCD, when you start busting out the Feynman diagrams, now all of a sudden your alpha is not a tiny number, but instead it's actually something that sticks around longer and makes your higher order Feynman diagrams more and more relevant. Especially as you go to the low energy limit, now all of a sudden you really have to factor in this combinatorial explosion of different high order Feynman diagrams, and the whole thing becomes an absolute mess to work with. And so in order to do anything with quantum chromodynamics, you pretty much have to use computational methods like lattice QCD, which is where you apply these equations to a lattice of spacetime points. In some contexts, you can also resort to like an effective field theory. And, for what it's worth, if you're at very, very high energy scales and alpha S becomes small enough, then perturbative techniques do start to become a little bit more relevant in that context. Well, anyway, so that's the strong coupling constant. It's a pretty big number, and it's bigger at low energies and smaller at high energies. So yeah, anyway, that's a few words about the running of the strong coupling constant. And you know what? This is actually a good time to segue into a comparison between electromagnetism and the strong force, so we can understand their similarities and differences, and so we can understand gauge theories more generally. Alright, so having explored quantum chromodynamics, I want to take a moment to compare the structural similarities between electromagnetism and the strong force, so we can see how gauge theory gives us a very coherent and unified way to think about these two very different forces. So I've listed out a bunch of properties of electromagnetism as well as the strong force, the things we've talked about in this video: the matter field, the gauge group, the gauge field, field strength tensor, the Lagrangian, so on and so on. And so I want to go through each of these things and see, are these actually kind of the same thing? Is there a way to generalize each of these concepts? Well, first of all, if you look at the gauge group, for electromagnetism we have U1, and for the strong force we have SU3. Now those are different things, but in both cases we have a compact Lie group. So both electromagnetism and the strong force blossom from a compact Lie group that we might as well call G. Now for electromagnetism, the gauge field is the photon field, whose components are real valued, that is, they live in the Lie algebra of U1. And for the strong force, the gauge field is SU3 matrix valued. So in both cases, we have a gauge field which is a 4-vector field whose components live in the Lie algebra of the gauge group. We call that little g. And the same goes for the field strength tensor. For electromagnetism, the components of the field strength tensor live in the Lie algebra of U1, and for the strong force, the components live in SU3. And so once again, we find that in general, the components of the field strength tensor live in the Lie algebra of the gauge group. Now, if you look at the Lagrangian, you find that it basically has the same form in both cases. You have the Dirac Lagrangian, you have an interaction term, and you have this F mu situation for the energy of the gauge field. So we find a deep structural unity in the Lagrangian. Now, of course, electromagnetism only has one field strength tensor, whereas in QCD we have 8 real-valued field strength tensors. But in general, we can write the Lagrangian as summing over A, where for the strong force, A runs from 1 to 8, but for electromagnetism, A is just equal to 1. Now then the question comes up about whether the gauge field has self-interactions. In electromagnetism, the answer is no, but in the strong force, you have these 3 and 4 gluon vertices. And even though this seems like a pretty irreconcilable difference between QCD and QED, we can generalize it by saying that if the gauge group is abelian, then the gauge field will not have self-interactions, but if the gauge field is non-abelian, then it will have self-interactions. So even that difference between QED and QCD can be understood in the context of gauge theory. We have this notion of a gauge covariant derivative, which is simply the partial derivative plus I times the coupling constant times the gauge field. And as far as the gauge transformation rules, in both cases the matter field psi transforms simply as U psi, where U is a field of elements that live in the gauge group G. In electromagnetism, that's e to the I theta, and in QCD, those are SU3 matrices. But in general, psi bar is U psi. And as we saw earlier, the way the gauge field transforms is actually exactly the same for electromagnetism and the strong force, in that the equation for the strong force, if you substitute in U equals e to the I theta, gives you exactly the equation for the photon field that we derived in the electromagnetism video. And the same is true of the way the field strength tensor transforms from one gauge to another. In both cases, the field strength tensor undergoes the adjoint transformation. But because electromagnetism is based on U1, which is an abelian group, the adjoint transformation is trivial. And so you see that there really are these tremendously deep and profound structural similarities between electromagnetism and the strong force. And these similarities apply in general to other gauge theories. So for example, if you look at like a grand unified theory based on SU5, then you go through this list and these things still apply. You're going to have a gauge field whose components live in the Lie algebra, and you're going to have a field strength tensor, and so on and so forth. Now, in a grand unified theory, you're also going to have extra Higgs fields that break down the gauge group into the observed gauge group of the standard model. But let's not get into that today, okay? That'll take us too far afield. Now, there is a profound difference between electromagnetism and the strong force, which is that the strong force is much stronger, as the name suggests. The strong coupling constant is very different from the fine structure constant of electromagnetism. All right, let's go ahead and wrap up this series with the surreal reflection on the nature of matter and energy. Okay, so you may have heard of a little something called E equals mc squared. And, this equation is basically synonymous with Albert Einstein, because he was the one who figured this out. And what the equation means is that any mass actually contains energy with a proportionality factor of the speed of light squared. And another way to look at this equation is to divide by c squared, and you can write it as m equals e over c squared. And of course, this is just the same equation. But when you look at it this way, you can say, whoa, if you have some energy, E, that's bound, then that's going to have mass. And to calculate the mass of the bound energy, you just divide it by the speed of light squared, which is about 9 times 10 to the 16 meters squared per second squared. So that's a huge number. So when you divide energy by a huge number, you get a pretty small number. And that's why bound energy, even though it does have mass, doesn't have very much mass relative to how much energy it has. Now, when people think about this equation, E equals mc squared, they usually think about it in the context of nuclear energy or nuclear weapons. But actually, it's as true for the nuclear stuff as for a cup of coffee and all the other things. So for example, if you take the biggest nuclear weapon ever detonated, the Tsar Bomba, it released about 2.1 times 10 to the 17th joules of energy. Divide that by the speed of light squared, and you can see that that's 2.3 kilograms of mass that was converted to energy. Now, 2.3 kilograms of mass doesn't sound like a whole lot, but what if you say it this way? You're basically talking about 5 pounds of light. Like, you know how much light you need to have the equivalent of 5 pounds of stuff worth of light? I mean, it doesn't even make sense. Like, if I am holding 5 pounds of potatoes, I might have an armful of potatoes, but that's not light. Light doesn't weigh anything. It has momentum, it has energy, but it doesn't have any mass. So this idea that you're going to take 5 pounds worth of material and just completely delete it from existence, well, not really deleting from existence, right? You're just releasing it, letting it go from a bound state to a state where it's able to radiate out explosively. And that's just crazy to have that much mass that gets converted in an instant into pure energy. I mean, that's like terrifying. But then if you consider something as mundane as a cup of coffee, let's say it starts off at about 90 degrees Celsius and then cools down to room temperature, about 20 degrees Celsius. Well, as it cools, it's going to release approximately 7 times 10 to the 4 joules of energy. assuming an average-sized cup of coffee. And if you divide that by the speed of light squared, you get 0.8 nanograms. Now, of course, that's a tiny, tiny amount of mass, right? No one would notice that, but it is there. And a hot cup of coffee is actually heavier than a cool cup of coffee, just because of the difference in thermal energy. Now, in reality, the amount of water vapor that's evaporating as the coffee cools has a way bigger effect on the mass than this whole thing about thermal energy. If you were to have two of the exact same cups of coffee, but one of them is at 90 Celsius and one of them is at 20 degrees Celsius, there is going to be a tiny little 0.8 nanogram mass difference between those cups of coffee. But because the amount of energy is so small, the amount of mass is like super duper small. It's small divided by the speed of light squared. And, just as another example for the electric car enthusiasts out there, if you have a Tesla with a 100 kilowatt hour battery pack, well, 100 kilowatt hours is going to be 100,000 watt seconds, and a watt second is a joule. So you're talking about 3.6 times 10 to the 8 joules of energy between when the battery is dead and when the battery is full. Well, that's a whopping 4 micrograms, which is actually not very whopping at all. That hardly whops. Maybe on the nanogram scale, but no, you would never notice 4 micrograms. However, this does teach us that if you drive with your battery low, then your tires are going to last just a tiny little bit longer because they'll have less weight on them. No, that's terrible advice, of course. Okay, 4 micrograms does not make a difference at all. But it doesn't make zero difference, you know what I mean? It makes 0.000 something of a difference, but... Well, anyway, so all I'm getting at here is that bound energy always has mass, but it's typically a very small amount of mass. But then the question comes up, hey, wait a minute. As we've been talking about in this video series, there's a whole lot of energy bound in the nuclei of your atoms. Remember how dense they are, remember how intense everything is in there with your quarks bound by your gluons, and you've got this tremendous amount of potential energy and kinetic energy of the quarks all tightly bound together. And so then the question comes up, given that we know that the nuclei of our atoms contain a tremendous amount of this energy that we can attribute to QCD, right? The energy that blossoms from local SU3 symmetry that's in the nuclei of every single one of our atoms. Well, we can ask what percentage of our mass can be attributed to that energy. It's a very interesting question, because you think about it, it's like you're made out of stuff, right? Like material stuff. So this idea that some fraction of your mass might actually be attributed to the energy that blossoms from local SU3 symmetry, it's kind of a trippy concept to think about. I mean, if you flail around or if you hop around and you can kind of feel your mass, like if you move your arms back and forth real fast, you kind of get a sense of the inertia of your mass and you can kind of feel your physical substance and your physical essence, And it's like, okay, how much of that is just pure bound quantum chromodynamics energy? Well, we would think it should probably be a small number, right? Like if you think about it, let's say 1% or 2% of your mass comes from this QCD energy. Well, in a human body, 1% or 2% of your mass, that's a few pounds. Imagine if a few pounds of your body was just pure energy. That'd be pretty crazy, huh? But get this, it's not 1%, it's not 2%, it's not 3%. No, 99% of your mass is pure QCD energy. I know it's hard to believe, but it is what it is. So, just sit with that fact for a while because it changes your whole perspective on life. And this leads to the final line of this video, the mic drop moment, which is that, my friends, to a good approximation, you blossom from local SU3 symmetry. Hey, I want to say thank you to everyone who has been supporting the channel on Patreon. Throughout this QCD series, a lot of new people have been signing up, and I've reached that threshold of survivability, and it's looking like I might actually be able to do this full time. So I can't tell you how grateful I am for that. Thank you all so very much for helping to make this dream come true.
We started with local SU3 symmetry.
Yo, it's the octopus.
What a magical principle. Oh, how it blossoms magnificently into the Lagrangian of QCD. Oh yeah, the strong nuclear force as a gauge theory. Thanks for watching.